Hello, Geography 232 students. Welcome to our first lecture, Analysis and Modeling. So by this time, I hope you've had a chance to review the syllabus for the course. I've gotten comfortable with our Canvas class, and if you have had any questions, hopefully you've reached out. If you have not, feel free to send me a message through email or through Canvas Messenger, and we can get things sorted out. So for our first lecture, we're going to be talking about just an introduction to raster imagery. It may be a review for some, it may be new information for others, and then we'll touch on spatial analysis. What is spatial analysis? And lastly, I'll wrap up with a review of ArcGIS Pro. I'm assuming most of you have had exposure to ArcGIS Pro at this point, but if you haven't, that's okay. This class will be solely run on Pro. We're not going to be using any ArcMap at this point. So if you have questions about anything, obviously reach out, let me know. You can post questions on the discussion board, or like I said, send me an email or a message. All right, so let's get going. So this week, we will talk about what are raster data, compare and contrast raster versus vector data, talk about two different types of raster, continuous versus discrete, get into spatial resolution, how is it important in the context of spatial analysis, what is spatial analysis itself, and lastly, like I said, wrap up with a review of ArcGIS Pro. And if you are already, a pro at Arc Pro, feel free to skip the last section. It would mostly pertain to those that are just coming to the software, either fresh or needing a quick review. All right, so quickly, data models, looking at the difference between vector versus raster. So if you're coming to this class having completed Geography 230 and or Geography 231, you've had full exposure to vector data. Vector data are best understood as points, lines, and polygons. Maybe your exposure to raster data has been a bit limited at this point. So that will be the primary focus of the first 2/3 or 3/4 of the class will be raster analysis, and then we'll get into some modeling using Python and Model Builder. So vector data, points, lines, polygons. The goal of all GIS data and maps in general is to represent the real-world objects as accurately as possible. And so whether it be raster data or vector data, the goal is the same. Okay, but we have two different basic approaches. Vector data, as I said before, are discrete data stored as points, lines, and polygon features. With a point, line, and polygon, you can pretty much represent the entire face of the Earth, and at different scales, right? So the example I tend to use is a city can be both a point or a polygon, depending on the scale. So if you are looking at a globe, the city of Los Angeles is best represented as a single point because of the scale. If, however, you're zoomed into Southern California, the city of LA is best represented with a polygon. Okay, so points, lines, and polygons are often interchangeable. Lines are sort of a bit different. Those obviously are going to be representing linear features, but scale is key in determining the geometry type, point or polygon in this case. Raster data are stored as essentially an array of cells. Okay, so contiguous data are stored as a gridded array of cells. And the best way I tend to explain this is just to think about taking a photograph with your phone and then zooming in as close as you can. The closer you get, you tend to start to see pixels, right? So a pixel is essentially the same thing as a cell in this case. It's a matrix. You have an X, Y axes. And along those axes, you have various points. In this case, these would be cells or pixels, and each cell represents some numerical value. I'll get into greater detail in a bit, but essentially, each cell stores a value for a specific location on Earth, or maybe it's the moon, or maybe it's Mars, but some remotely sensed location. So, vector versus contiguous raster data. Raster formats store data in contiguous cells. In contiguous, in this context, what we mean would be cells that are adjacent to one another. So continuously changing. Contiguous means side by side, right? So elevation, precipitation, temperature, imagery, these are all different data representations that can be stored as rasters, okay? So if it's elevation, each one of those cells is going to represent an elevation, right? So some measured height above sea level. If it's precipitation, each cell is going to represent some measured value of water, right? Maybe it's inches of water, centimeters, what have you. So our map here to the right is a representation of precipitation. You can see the darker colors, the green and the blue, represent higher amounts of precipitation through the equatorial region, both in Central and South America, also Southeast Asia, right through Sub-Saharan Africa. The other giveaway there would be the darker color above the Pacific Northwest, as well as the Gulf Stream current, which tends to bring warm water up along the east coast of the United States. So we've got contiguous raster on the bottom right, and we have discrete raster on the bottom left. In discrete, what that essentially means is each feature is discrete amongst themselves. So we have a road does not feed into an adjacent road, right? Each road is its own thing. Okay, it's its own object, and in that sense, it's more similar to vector data. But again, we're talking about just raster. So imagery itself, photographs, as I mentioned earlier on, are also types of rasters. This is an example of a raster layer, looking at elevation. So raster data, also known as surfaces. A raster has no distinct shape. It can be rectangular, as the example on the right. It can also follow the shape of any other particular layer it's been clipped to. So you could have a raster the shape of Los Angeles County. You could have a raster in the shape of a circle, square, what have you. They have no distinct shape. What they are a surface of measurable values, as explained prior to this. Each matrix is composed of identically sized squares, also known as pixels or cells. Each cell represents a unit of the surface area and is measured or estimated as a value for that specific location over the Earth, or what location you may have. And data are displayed using gradients to show change from location to location. Maybe that color scheme is light to dark, so white to black, maybe it's red to blue, orange to yellow, what have you. But in order to make sense of the data, whether it be an actual representation of the Earth's surface, or precipitation, or temperature, or burn probability, or what have you, you'd want to choose a color scheme that is appropriate for that context. And so rasters are georeferenced. There is an XY location, but it's generally from some specific origin in the actual surface itself. So maybe it's the upper left corner, the bottom left corner, and then each cell essentially goes out from that origin point. So unlike a vector polygon, which can contain virtually limitless numbers of points or data fields, each cell in a raster has only one single attribute, and that's its value. And that value, again, can represent elevation or temperature, precipitation, or any other sort of measured or interpolated value, but there can only be one. Okay, so if you have a data set that has a whole bunch of different attributes, like let's say it's roads. Going back to the slide a couple ago, and we saw that the highways next to the precipitation data. If you want to have the road name, the road type, the miles traveled per year, any sort of number of attributes greater than one, you want to use vector data. You want to stay away from rasters. Rasters are really great for a specific purpose, but it's not necessarily for storing lots and lots of attributes. It's about a single attribute that can spread over a broad surface. Okay. So the value represents some property, as I said before, and values may be integers or floating point numbers, so they don't have to be whole numbers. One thing to keep in mind is that imagery differs from analytical raster data. An analytical raster stores information in a cell that can represent some of the examples I said before. A measurement within the cell, so it could be precipitation, or it could be temperature. It could be an inventory or account within that cell. So let's say you've got a series of points, like vector data points, and you want to essentially find out what the density of those points is. You can do a count by some predetermined cell resolution, and you can find out what the density is. And then you end up with a surface. So instead of having a whole bunch of points on a map that may get cluttered, you can convert that to raster data and then get a clear representation of what the density is over that surface. And it's stored in a geographic or map projection coordinate system. So if you take a picture with your phone, it's not necessarily going to represent a specific location, whereas actual analytical raster data always has some sort of coordinate reference. It represents a location on the surface of the Earth. For imagery, the cell is called a pixel because its data is not necessarily restricted to the boundaries of the cell. Imagery is a sampling of radiance of light along the electromagnetic spectrum at a geographic location. Every image has its own unique geometry that is related to the Earth with a sensor. So raster data usage. What are some uses that we can get out of raster data? Hydrological modeling, elevation measurements, solar radiation measurements, slope analysis, bathymetry, essentially the surface of the seafloor, or map algebra, where you can actually take two different rasters and find out how they differ, how they may stack upon one another, and that's great for actually running spatial analysis with rasters. A couple of visuals here. We've got density, the example we gave prior with point data. This would be cities here on the left. That would be cities by density. So you can either have a whole bunch of points on a map, or you can convert those to raster and then actually get a good visual representation of where the highest density of cities may be. Okay, least cost path. That's an interesting one, where essentially the numbers on the raster represent elevation, and then you can calculate what the least cost path, or the easiest way to get from point A to point B, is taking elevation into account. Viewshed, buffers, interpolation, distance, those are all potential uses or functions of raster data. So two different types of rasters, continuous and discrete. As I said before, continuous is essentially a continually changing surface. Maybe that's elevation, maybe it's temperature, maybe it's precipitation over the surface of the Earth. Discrete data, as the name implies, every single raster portion is discrete from another. And that may be useful in the context of land use management, land cover, where each portion of the Earth represents a specific land use type. So you've got, from maybe a planning perspective, you've got single-family residential, multifamily, commercial, industrial, and so on. So that might be represented there on the right. Continuous raster data, it's where the raster stores surfaces or fields of variables that change continuously over space. My example obviously was elevation, and what we're looking at here on the right is a DEM, also known as a digital elevation model. It has many potential values, but each value tends to be close to a similar value. And that's just like if you think about the surface of the Earth. If you move from point A to point B, if point B is close to you, it's likely going to be a similar elevation. If point B is far away, it may be a very different elevation, but moving continuously from one place to the next is going to be a slowly changing gradient. And here's that DEM with greater detail and a legend. So a digital elevation model has cells or pixels, each of which contain a single elevation. Regularly spaced arrays of cells, when visualized with a color scheme, an appropriate color scheme, can give you a more or less a kind of a proxy for what the Earth's surface looks like. Even though it's not actually a photograph, it represents elevation. We use certain colors that kind of trick our brain into thinking or recognizing a pattern that we'd see on the Earth's surface. So in this example on the right, we use light green to dark green to yellow to orange to red to brown to white. And obviously, highest elevations, we tend to think about snow. Lower elevations, we tend to think about grasses and fields like that. And so we use sort of a logical color scheme to sort of trick the eye into thinking we're looking at an actual photo, but it's just elevation. So raster images are stored in bands. Raster images may be single band or multiband. All right, and so multiband is where we start talking about hyperspectral imagery, which we'll get into next week. Single band images are, as the name implies, just a single color band. In this case, they are a representation of a numerical value from 0 to 255. We call them DN, or digital numbers. And so the image values represent brightness, reflectivity from the Earth's surface. And so even though it's a single band image, obviously it's going to be black and white, but you can still make out features on the Earth's surface, especially at a given resolution. The first three bands in a multi-band composite image are blue, green, and red. As you go on increasing the bands, you tend to get to near infrared, and several other different bands that we will get into. And those are useful for not just visually representing what the Earth looks like with the naked eye, but also seeing other things like moisture, the health of vegetation, looking at other features like underneath the surface of water with bathymetry, and a handful of other types. And so infrared as well, looking at heat signatures. So these multi-bands are useful for remote sensing, not just what the Earth looks like with the naked eye, but pulling out other information that is not necessarily visible with the naked eye. So there are near infrared, mid-infrared, and thermal bands as well. So there are three main ways to display single band rasters. That's as a binary image where every cell represents either a 0 or a 1. Grayscale, where, as again I mentioned the 0 to 255 digital numbers. That would be an 8-bit image. With an 8-bit image, that's 0 to 255 digital numbers, or a 16-bit image is 0 to 65,535. These are often used for grayscale aerial photos. And lastly, you can have actually a color image from a single band raster using a color map. So a set of values is coded to match a defined set of red, green, and blue values. And so even though it's a single number from the single band, those can be translated to RGB values. Multiband imagery, on the other hand, as the name implies, it covers multiple bands along the electromagnetic spectrum. So every cell location has more than one value associated with it, and that's best understood with the stacked rasters there on the bottom left. So each raster represents a specific band along the electromagnetic spectrum, and they tend to be, at a minimum, red, green, and blue. And as I mentioned before, you might have infrared, ultraviolet, near infrared, and so on. So the term band originates from a reference to the color band on the electromagnetic spectrum, which is visualized here. So as you may be aware, the human eye can only see from essentially about 400 nanometers to 700 nanometers along the electromagnetic spectrum. And that basically means that, we can see reds, greens, blues, yellows, oranges, violets, but there is a broad swath of the electromagnetic spectrum that we cannot see with our naked eye, but can be sensed with special sensors. And those would be very long wavelengths and very, very short wavelengths. You've heard of X-rays, gamma rays, microwaves, and so on. So we can use special sensors to actually get an eye on those wavelengths and then visualize them through GIS. So just this is really just kind of for your own reference to get kind of a comparison to understand what these wavelengths, how long these wavelengths actually are. So the visible segment of the electromagnetic spectrum covers about the size of a bacteria. It's very, very small. As you get along these longer wavelengths, where we find radio waves, AM, FM, and so on, the wavelengths actually can be the length of a soccer field or a house. On the other end, these very, very, very short wavelengths would be gamma rays, and those are incredibly small, very, very small. Visual representation of your RGB. You combine those three bands together, you end up with a composite image that looks approximately like what you would see with the naked eye. So with RGB, or a multi-band image, you can see that still, if you break it down by color, we'll go with red, for example, it's still an 8-bit 0 to 255 digital number image, okay? And so it's reflectivity within that single red band of the electromagnetic spectrum. And so in the image, you can see one section, it may have an R value of 57. If it's a lighter color, if it's a darker color, it might have an R value of 7. With green, if it's a high value, it's going to have maybe an example of 228 or something lower, and same with blue. So even though we're talking about multi-band imagery within a single band, we're still talking about that 0 to 255 digital number. So resolution, as I mentioned before, using the example of an image taken with your cell phone, if you zoom in too much, you tend to see those pixels, right? So it's the same thing with raster imagery. Cells in raster vary in size. The cell size determines the spatial resolution, and essentially what you're looking at is the cell has some sort of a real-life size resolution. And so one cell might represent 90 meters on the surface of the Earth, maybe 10 meters, maybe something smaller. With more recent satellite imagery, we tend to see like 1-foot imagery, even 6-inch or 3-inch imagery, which is incredibly high resolution. So 1 pixel on the image represents only 3 inches on the surface of the Earth. With resolution that high, you can make out people and the color of a person's hair even. It's pretty incredible. So cell size determines the spatial resolution. A smaller cell size leads to more detail, but also a greater file size. Larger cells, less detail, but smaller file size. And depending on what your purpose is, maybe low resolution is okay. So cell size must align with the application requirements. If you're doing a lot of remote sensing, low res imagery is fine. If you are a CIA intelligence officer, you probably want high resolution. So here are a couple of examples. This is 12-inch, obviously 1 foot res. So 1 pixel represents 1 foot on the ground. So you can see actual physical features here. Pavement, obviously. You could make out airfields, soccer fields, things like that. You could tell agricultural area from a wildland. Buildings, hydrology like streams and rivers and creeks. What sorts of uses would you use this for? Urban planning, change detection, looking to see how the surface of the earth has changed over a period of time. Prevailing land cover, as I mentioned before, is it grasses, trees, water, what have you? Forestry management, looking for clear cutting patterns, health of the forests, things like that, wildfires. Here we have 6-inch, so 1 pixel equals 6 inches in the real world. Features you can see: sidewalks, dirt roads, parking lots, driveways. You can see utility poles. Obviously, you can make out cars. You can't really tell what type they are, but you can see the color. You can see more or less the size. In this case here, this might be useful for identifying land boundaries. Let's say there's a property dispute. You might want to have a higher resolution image to tell where a property line is. Irrigable land cover, natural resource management, things like that. And finally, we've got 3-inch resolution. At this resolution, you can actually make out vehicle types. You can see I can identify 2 pickup trucks in this image. You can see one car has a sunroof. Obviously, you can tell the colors. You can make out the foliage on the trees. In theory, you'd be able to view where fire hydrants, manholes are. You can see where the curb ends and the sidewalk begins. This is useful in 3D modeling, civil engineering, and any sort of industry where a high degree of resolution is important. So where do we actually find out what the cell size is? Well, if you go into the raster layer properties in ArcGIS Pro, you right-click and go to the properties, you'll see a linear unit. In this case here, the resolution is 1 meter. You can see meter 1. Okay, and so if it were half meter, it would be meter 0.5. If it was a foot, it would be 1 foot. So at any rate, you can find out what the resolution is there in the layer properties. All right, what is spatial analysis exactly? What is spatial analysis? First, what is spatial? One of several terms often used interchangeably across different scales. So people often use geographic, spatial analysis, geospatial interchangeably. Each one has more or less a specific application depending on the context. So geographic, it would be anything that occurs on the Earth's surface or near the surface, so not necessarily on the surface itself. So if we're talking about weather and climate, that's still a geographic concept, even though it occurs near the surface, not on it itself. Spatial refers to any space, not just on the surface of the Earth. It could also be in your bedroom. It could be on Mars. It could be on Moon. Anywhere where there is an X, Y, and Z location, that is spatial. It refers to space itself. Spatial analysis, that's the application of analysis techniques to geographic and non-geographic spaces. So you can run spatial analysis on the surface of the Earth or within your household, right? So like how many people per room, that would be a type of spatial analysis. And lastly, geospatial, that's a subset of spatial applied specifically to the Earth's surface and near surface. So geospatial research or geospatial analysis would be about the spaces that are measurable and sensed on or near the Earth's surface. And why is spatial special? So almost all human activity and decisions involve a spatial component. Anything that happens on Earth can be measured essentially if there is some sort of a spatial component. Crucial to understanding both physical and human geography, for example, modeling elevation or modeling population density. So those are 2 very different concepts, right? One involves mountains and sea level and actual things you can touch and feel with your hands. The other involves a sort of a little bit more kind of amorphous concept like population density. But you can still model that and run spatial analysis on there because it's all about a numerator and a denominator, right? So when it comes to population density, your numerator would be the number of people, the denominator would be within some boundaries, right? So it all comes back to spatial boundaries. How many people in the county of Los Angeles? How many people in the state of California? How many in the United States, right? So if you want to talk about density, you'd look at people per some predetermined geographic unit. Maybe it's square mile, persons per square mile, persons per square kilometer, what have you. So working with geographic information involves unique, complex, and often difficult choices. For example, they are multidimensional, as I said, need to have an X, Y, and Z value. So getting the location right can mean the difference between life and death, or money wasted or money saved. So if we're talking about search and rescue efforts, precision is very important, right? If we're talking about investments of some sort of like maybe a power utility company to build, we'll say underground cables in a specific location, that's a very high cost investment. So location is key. It may be represented at different scales from very small areas, for example, 1 to 500, where 1 foot on a map represents 500 feet in the real world, to very large areas where 1 foot on a map represents 100 million feet in the real world, right? So spatial analysis relies on scale. And lastly, it may be collected, used, and shared by private citizens, governments, companies, and so on. So moving towards, we are trying, as a society, trying to move towards more freely accessible and limitless data access. So you've heard the term big data. Data science and geospatial science are huge and continually growing fields. And that's because our ability to collect and store data has grown exponentially in the last 30, 40 years, and will continue to grow in the future. So some of the biggest problems on Earth are best understood spatially: climate change, natural disasters, war, population dynamics, and so on. So just a couple examples here. On the left, we have world population in 2017. That would be, it looks like a population, not density, but actual raw population numbers. On the right, we have the path that Hurricane Harvey took in 2017. And then in the middle there, we have the extent of ISIS in 2017. And so even though these are massive problems, or the problems or issues to be solved, they can oftentimes be analyzed spatially. Okay. So spatial analysis is the process by which we turn raw data into useful information. This includes methods applied to geographic data that often add value to the data. They help us make and support our decisions, and they often reveal patterns and anomalies that may not be immediately obvious. So spatial analysis is about not just the raw data that's been sensed or collected, it's about how we can draw information from that raw data. So the analysis portion is what converts it from raw data to actual actionable information. So spatial analysis is a set of methods whose results change when the locations of the objects being analyzed change as well. They are location dependent. So if you run an analysis, if you're a power utility company and you run a cost analysis in a given location, that cost analysis is only good for that location. If you change the context, the geographic context from, we'll say, a mountainous region to a desert region, things are going to be different there, right? The geographic location changed, and so the choices being made and the data inputs change, and therefore the conclusions change as well. Some of the earliest documented spatial analysis was done in the mid-19th century by a British doctor named John Snow, not the one from Game of Thrones. He mapped a cholera outbreak in London's Soho neighborhood, and anywhere where there was a case of cholera, he essentially put a dot on a map. And so in this context, the dots were the raw data, right? He went out, collected locations, put them on a map, had a suspicion that maybe there was some sort of spatial component to this cholera outbreak. As he started to map the locations of these outbreaks, or these cases rather, he realized a pattern that was essentially around the Broad Street water pump. So it was a water pump. At the time, cholera was thought to be an air disease, like a miasma, a disease that floated through the air, but it actually is waterborne. It wasn't known at the time. And so he essentially surmised from the location, the proximity of the cases to the water pump that, sure enough, cholera is a waterborne illness. And so this was an early use of spatial data in analyzing a seemingly non-spatial problem. And this is just a redrafting of the John Snow map, the very famous John Snow map, just to kind of make it a little easier to understand. But essentially, John Snow did some of the earliest spatial analysis. So reasoning and spatial analysis. Spatial analysis can be either inductive or deductive. So inductive reasoning is when you examine empirical evidence in the search for patterns that might support new theories or general principles, in this case with regard to disease causation. So John Snow practiced inductive reasoning. He might not have had a wholly formed theory or hypothesis. He went out and started collecting data through observation. He made observations, he noticed a pattern, he drew up a hypothesis, and his theory was cholera is a waterborne illness. So now we can actually take that and then apply deductive reasoning. Say we have a theory. The theory is that the water pump is the source of illness, and then that will be the hypothesis. We'll test that hypothesis by maybe running a control experiment. Go check other pumps around London and see how many sick people are around those water pumps. If the number is 0 or close to 0, whereas the other pump is very, very high, that would either confirm or more or less either confirm or reject this hypothesis. And so while John Snow relied on inductive, you could then take that hypothesis or that theory and apply deductive reasoning. So inductive reasoning draws general principles from specific observations. Conclusions are essentially drawn from data and findings with a degree of uncertainty. Deductive reasoning draws specific conclusions from general principles or premises, in this case that the water pump is causing the illness. And conclusions are certain provided all the premises are true. In this case, that the sick people tend to only be located nearby this particular water pump. And at other water pumps, there are no or very few sick people. So here is spatial analysis in action. Now, typically I do this in a classroom and I ask students to take some guesses about what this map represents. There's no title on the map. There is a legend, but it doesn't actually tell you what we're looking at. So I would encourage you at this point, if you need to pause the video, just spend some time looking at the map, spend some time looking at the legend that says age-adjusted rate, significantly high in and not in the highest decile, in the highest decile, not significant, and so on and so forth. And so I will just kind of cut to the chase at this point. We'll take away the covers. This is cancer mortality in the mid-20th century by county, specifically trachea, bronchus, and lung cancers. And so I always ask students, what is the spatial pattern here, and what might be leading to higher cases of cancer in these areas? And so generally answers are, well, maybe proximity to industrial activity. Yes, sure. Maybe smoking activity. Maybe. Maybe ports. That's one that's come up several times. You see down there in Louisiana, along the Northeast, along Florida, the San Francisco Bay Area. Could be. I don't actually know the answer, but it's interesting to look at the data and try to draw conclusions using inductive and then maybe deductive reasoning. So what are our conclusions? Spatial analysis is the process by which we turn raw spatial data into useful information. And spatial data can be interpreted in many different ways, either inductively or deductively. All right, so this last section is a review of ArcGIS Pro. If you already feel very comfortable with Arc Pro, you can skip this section. This is more for newcomers to the software. These slides are fairly old, but the concepts and the principles of Arc Pro have not changed. ArcGIS Pro, it was originally a fusion of 3 different applications: ArcMap, which is sort of the predecessor to Arc Pro, ArcGlobe and ArcScene, which allowed the visualization of 3D data, and City Engine, which is primarily a urban planning tool. It is more or less the merging of those 3 separate applications into one, and it is more or less quickly becoming the industry standard. So Arc Pro, it's GIS designed with modern computers in mind. This is obviously new at the time. Arc Pro made its debut, I want to say, in 2014 or 2015. So it's a new graphics engine, relied on DirectX, allowed for anti-aliasing for smoother 2D and 3D graphics. Integrated into ArcGIS Online. So Arc Pro's greatest benefit, in my opinion, is its integration into Arc Online, which is the cloud, essentially. And so with just a simple username and password login, you can save your data online, you can share it with others, you can pull data from the cloud, visualize it, and so on. And that's the way that you all will be using the software. So with a username and password that I will give you. It's 64-bit, multi-threaded, and it allows for multi-core processing, which in theory allows for faster, more reliable processing over ArcMap. Although I will say, in my experience, it has slowed down quite a bit in the last couple of years as Esri has packed more features into the program. And it uses a more or less familiar user-friendly interface, the ribbon and tab interface that's familiar in Windows. So across the tab, we'll see core tabs: project, map, insert, analysis, view, edit, imagery, and share. Those are your core tabs. There are others, which are known as contextual tabs. Those are tabs that appear in certain contexts. And examples of those, like if you're changing the symbology or labels, things like that, you'll see a appearance or label or data tab that will show up in certain contexts. These are just more or less useful for the lecture notes so that you've got an idea what these all stand for. This is how to pan and zoom. Again, I'm going to skip through this verbally, but you can take your time looking over these in the lecture notes if need be. Analysis in Arc Pro. So the most common tools are under the Analysis tab. You can always search for tools by clicking on geoprocessing and searching for there's over 250 tools. Model Builder, which we'll get into toward the end of the semester. There's a Python window for customizing scripts. Network Analyst is an extension for routing and directions. And Spatial Analyst is one we're going to rely on in this class quite a bit for raster analysis. Another key difference between ArcMap and Arc Pro is editing. So in Arc Pro, we call it WYSIWYG editing. What you see is what you get. There are no editing sessions. If you are an ArcMap user, you'll know that you have to start an editing session, save your edits, and end your session. In Arc Pro, every layer can be edited at any time. You still have to save those edits, though. Okay. Again, I'm going to skip over this. You can review it in your lecture notes if need be. 3D maps, another key addition to Pro that was not available in ArcMap. So maps, also known as scenes, those allow for either a local or a global scene. Global scenes are kind of looking at the data from a Google Earth perspective, whereas local scenes look more like a map, but they can be tilted and viewed in a 3D environment. Here are some helpful shortcuts. And that is the end of this lecture. So in our face-to-face time, I will hand out Geography 232 specific usernames for each of you and passwords, and so then you can start using ArcGIS Pro on your own. So thank you for your time. Best of luck this semester. Take care.